In business, the modern spreadsheet operates as a lightweight relational database, a logic processor, and a visualization engine. Because it functions as a database, the integrity of business intelligence models relies entirely on strict functional architecture. The greatest threat to that integrity comes from fragile legacy habits, specifically poorly constrained lookups and unstable aggregations. A single fragile formula does not merely cause a localized calculation failure. It introduces systemic risk that silently spreads through entire corporate decision-making pipelines. We are going to deconstruct 3 specific architectural anti-patterns embedded in legacy spreadsheet design and rebuild them using robust, dynamic frameworks. Transitioning away from these legacy habits is the primary mechanism for preventing silent data corruption in enterprise-level models. At the base layer of any dynamic model lies the if function. It acts as a strict Boolean gatekeeper, altering calculation paths based solely on a true or false resolution. The syntax allows a user to omit the optional value if false argument, which introduces a severe vulnerability in numerical models. Without an explicitly defined false state, a failed logical test outputs a literal Boolean false into the cell. While functions like sum might treat this as a 0, functions like average ignore it entirely, instantly skewing downstream aggregations. When facing multi-tiered decision trees, analysts historically handled complexity by embedding if functions inside one another, a technique known as nesting. Excel permits nesting formulas 64 levels deep, a widespread architectural anti-pattern. Deep recursion creates spaghetti logic. If a syntax error occurs in the 30th nest, finding it within this dense fractal of colored parentheses is virtually impossible, rendering the entire formula void. The modern architectural alternative is the IFS function. IFS evaluates pairs of conditions and values sequentially. This shifts the calculation engine away from deep recursion and structures the logic as a flat iteration. Utilizing flat iteration eliminates severe syntax risk and restores immediate visual auditability to complex decision trees. Data analysis requires accurate quantification, which exposes a critical distinction between strict numeric counting and broader cell population tallies. The standard count function strictly iterates through a range and tallies numeric data. Count A, conversely, tallies any cell that is not technically empty. This creates an invisible hazard. Count A registers empty strings, represented by 2 quotation marks returned by a formula, as populated data. These visually blank cells artificially inflate dashboard counts unless targeted COUNTIFs logic is deployed to isolate them. Conditional aggregation functions like COUNTIFs and SUMIFs solve this by targeting specific criteria. However, they are bound by a strict operational law, geometric dimensionality. The calculation engine requires that all specified criteria ranges possess mathematically identical dimensions. Attempting to compare a 100-row range against a 101-row range forces a physical clash in the engine, resulting in an immediate hash value error. The architecture of SUMIFs also introduces a structural inversion compared to the legacy singular SUMIF function. Modern SUMIFs mandates that the sum range argument be front-loaded as the mandatory first argument rather than tacked on at the end. This front-loading anchors the aggregation target immediately. It removes operational ambiguity for the calculation engine before it processes up to 127 variable criteria pairs. Precise awareness of data types and strict adherence to dimensional alignment are non-negotiable prerequisites for accurate upstream analytics. For data retrieval, VLOOKUP remains ubiquitous. It is also an inherently fragile legacy standard. VLOOKUP's primary architectural flaw is its reliance on a static, hard-coded column index number to execute a retrieval. Consider a routine structural alteration, such as a user inserting a new column directly into the middle of a dataset. Because the formula remains hard-coded to column 3, it blindly extracts the newly inserted incorrect data without triggering a system error. This silent data corruption represents a severe risk to a financial model because it remains undetected while influencing high-stakes decisions. The professional standard replaces this with dynamic lookups, utilizing the combination of the index and match functions. This pairing entirely decouples the lookup logic from the retrieval logic. Match acts as a radar, finding the row position, while index acts as a mapping grid, pinpointing the exact intersection. This coordinate-based approach makes the formula resilient. If columns are inserted, the referenced ranges dynamically shift, tracking and pulling the correct data. Coordinate retrieval also delivers a massive advantage in computational performance. VLOOKUP forces the engine to load the entire table array into memory. Index and match interact strictly with the two specific columns referenced. Decoupled coordinate retrieval immunizes the model against structural dataset alterations and drastically reduces the memory footprint required for enterprise-scale processing. Data integrity requires strict sanitation. Deduplication is the precursor to accurate analysis. The standard remove duplicates tool operates as a static, destructive action. It physically, permanently deletes records from the source data. The dynamic unique function offers a modern, non-destructive alternative. Unique projects a distinct list of values into adjacent cells, preserving the raw data. But this projection requires strict layout discipline. If an obstacle blocks the path, the projection instantly snaps back and triggers a #spill error. Modern array errors like #spill or #calc act as environmental constraints that enforce clean data layouts. A common novice anti-pattern is treating all errors as nuisances by indiscriminately wrapping formulas in a blanket if-error function. This catch-all suppresses vital structural alerts. It hides deleted references and type mismatches, effectively masking the root causes of model decay. Defensive coding relies on targeted diagnostic handling. Using if-NA for lookups gracefully catches missing items, while allowing critical system failures to punch through and alert the analyst. Mastering Excel requires treating it as a rigorous architectural environment. By prioritizing coordinate-based retrieval, enforcing dimensional constraints, treating errors as precise diagnostic telemetry, professionals can transform fragile spreadsheets into bulletproof analytical engines.